Okay, so let us all welcome Sir Clark. Clark, yes, go ahead, Sir Clark. So
So,
the topic is about reasoning about programs. Take it away, sir.
okay, sir. Thank you, sir. By the way, good morning, classmates, and good morning, sir. So, our topic for today is about reasoning about programs, pre and post conditions, invariants, and correctness. Program conditions are the algorithms or code that can be documented with comments that state conditions that should be true when program execution reaches the point where the comment is located. So these comments are called preconditions, invariants, or postconditions, depending on their placement relative to a code or algorithm segment. So a precondition is a statement placed before the segment. It must be true prior to entering the segment in order for it to work correctly. So preconditions are often placed either before loops or at the entry point of functions and procedures. And the postcondition is a statement placed after the end of the segment. It should be true when the execution of the segment is complete. Postconditions are often placed either after loops or at exit points of functions and procedures. So an invariant is a statement placed in a code segment that is repeated should be true each time the loop executions reach that point. Invariants are often used in loops and recursions. So the program conditions like preconditions, postconditions, and invariant are not exactly a code. Oh, it serves as in some point it's a reminder or just an instruction, no? Hindi natin siya binabasa as a code. Hindi siya binabasa ng program as specifically a code. So we use it as a comment or yeah or just a reminder, no, before we start a program or before we run a program. So in an overview, what are the pre and post conditions, benefits of using pre-post conditions, writing effective preconditions, writing effective post conditions, handling invalid preconditions, and using the assert command. So what are pre and post conditions? No, preconditions are conditions that must be true before, before a method runs for it to work. And the post conditions are conditions that can be granted after method is finished. So for just documentation of executable code, like a contract with the user of your code. So like for example, no, I promise that if you satisfy all the preconditions of this method, then I will satisfy all of its post conditions. And no guarantee for behavior if preconditions not met. So benefits of using pre and post conditions. So insulates you from pebcock errors or problem exist between share and keyboard. So alam mo yung mga example ng errors natin na tinatawag natin pebcock. For example, no, you're just asking for integer, then si user, nagka-type siya ng string type. So error na po agad yun. No? Then it helps you design effective code. Then helps you write code that you know is satisfying. So in writing effective preconditions, so first we must specify necessary program states. So needed values for class variables. So ano yung kailangan nating values dun sa ating program. Then needed values for collaborating objects. And the second one is specify required parameter values. Like for example, kanina what I said, no? If you're asking for an integer, then the user must type an integer type. Or if you're asking a string type, the user must type a string type. And try to consider unexpected use cases, focus on extreme values of parameters, and put preconditions in the method comment. So yeah, we usually put the precondition and post conditions as a comment. So writing effective preconditions, ultimately preconditions are undesirable. Try to handle them in your method. Then if you handle a conditions, then it is no longer necessary to list it as a precondition. So in writing effective post conditions, so first thing to do is to specify resulting program states. Which class variables have changed? Which order programs objects have changed? So first in developing a program or in creating program, we must first input a data, no? Then how can we assure that the processing of the data is true. So, paano natin masabi na yung output natin, yung mismo yung hinahanap nating output. Paano natin malaman yung tama yung pagkakaprocess ng input natin into output? Then, specify method return values. Already doing this with at return. Then, don't repeat at return tags in a post condition. And put post conditions in the method comment. Yan. Several alternatives available. Throw an exception. So we can use an exemption command, no? Or yeah. Then which must be handled by calling method. Or we can just run and let things happen. But these options is not a good option, no? Then use the assert command. Only crashes if turned on. Then using the assert command. So using assert crashes the program by throwing on assert exception. And it only executes if the program is run with assertions turned on. So yan. We can use assertions, no? Pero make sure na naka-turned on yung ating assertion command kapag mag-run tayo. Like for we have the syntax assert boolean condition. For example, uh, yung condition natin is false, no? So we can run the assert exception. Yan. In object-oriented programs, the input and output of the method also include the object state before and after executing the method. So we have the specifications here, no? For example, yeah, preconditions is amount is greater than or equal to 0. So if our amount is less than 0, then we must use an assertion command. Kasi nag-false agad yung ating conditions. Bago preconditions pa lang, nag-false na tayo agad. So, hindi na agad natin mamimet yung desired outcome natin. Then, the post conditions, new volume is equals to old volume plus x. Then, for implementation, yan, we have the class water glass, int volume. So, volume natin ay value ay int. And void add water, double x. So, volume add to x. So, yun yung value ng ating new volume. So, si old volume plus x. Okay, JML is a system for annotating Java programs. So it requires preconditions and it ensures post conditions. So for example, like we have example earlier, class water glass. So we have volume and max as a double. And we have here the preconditions. This one is the preconditions. So requires volume plus the amount is less than or equal to max. So ibig sabihin po nito, yung volume natin and amount ng water dun sa glass must be less than or equal to the maximum. Or else, kapag greater than to the maximum siya kay max, mag-overflow yung ating glass sa water. So ibig sabihin, mag-error yung ating program or possibly na false yung lalabas sa ating conditions. So, for example, you're creating a program, like for example, a program that checks the area, no, of for example, area of your lot. So, i-check niya kung ilang gaano kalaki ba yung inyong lote, no. So, hindi ka pwede mag-enter ng values doon na negative. For example, yung length ng inyong area ay -5. So, it's already error, no, or mali siya agad before pa natin siya i-encode dun sa ating program. Mali na agad siya kasi in creating or in calculating the area of your lot, it must be first positive integer, no? Meaning kailangan from 0 greater than 0 or equal or greater than 0 yung value ng inyong length or ng width. Then for post condition, at ensures volume is equal to the old volume plus the amount. So yun, your new volume nyo must be equal to the old volume, then this amount na dinagdag niyo sa water. For example, you have a half glass or you have a 5 ml water or 5 milliliters in a one bottle.
500 milliliters of water in one bottle. Then nag-add ka ng 300 ml. So you have 800 ml, no? So make sure that your old or your new volume must be equal to the volume of your um, old volume of the water plus the amount. So dapat equal po siya. Or else, kapag di siya equal, so there's something error no dun sa program natin. For example, it must be a total of 800 milliliters, but the program said it's just only 700 milliliters. So dun pa lang meron tayong error, no? Yan. Void add water double amount. So this is the formula. Volume is equals to the volume plus the amount of water. So next is invariant. So invariants is are conditions that holds throughout the lifetime of a system, an object, or an data structure. So class invariant rule. So assertion P is a class variant for class or C if first is all public methods are constructors of C. Second, when applied to arguments satisfying the method's precondition. And the third is yield a state satisfying P or the satisfying assertion. Okay, an invariant is a property of the program state that stays true throughout the execution of the program. For example, oops. For example, the current volume of a glass is between to 0 and the maximum volume. So that's true. That statement is true. How can you say that the statement is a false? For example, the current volume of glass is between -5. So we can put -5 or negative values in the volume of a glass. And the maximum volume. So hindi tayo pwede mag-exceed dun sa maximum volume ng glass. What will happen if nag-exceed tayo dun sa maximum volume of a glass? So possibly mag-error na yung mag-error na yung program natin kasi nag-overflow na si water into glass. You can think of an invariant as both a pre and post condition on each method. So si preconditions kasi we indicate din on the opening part of our program, and the post condition kasi dun siya sa bandang dulo ng ating program, no? Then we can consider or we can think that invariant is both pre and post condition. So invariants in JML. So invariants are annotated with @invariant. For example here, so class water glass or an invariant 0 is less than or equal to volume, and volume is less than or equal to max. So if nag-false tayo dito, so therefore magkakaroon tayo ng problema dito sa the rest of our code, no? For example, if the invariant natin or the value is negative, magfo-false na agad siya dito kasi for example, invariant is -5 is less than equal to volume. That's false, no? So false and true is equals to false. So magkakaroon tayo ng error. So double volume invariant max is greater than or equals to 0. So the maximum volume of our water must be not less than to 0. Ayan, handling invalid input. So what we're gonna do if we're handling the invalid inputs, no, or if we encounter problems or errors during our coding. So what should we do when an input does not satisfy the preconditions? So first option, we have the lazy approach. Don't check for invalid outputs. So the second option we have is the self-confident approach, which will be return a default value on invalid inputs. Then the third option is pedantic approach. Use assertion to check for invalid inputs. So this is here's an example of our lazy approach. So we have the preconditions. We don't indicate preconditions. So ang pros dito sa example to is takes no extra export, and the condition is you have to be very careful when calling a method. So dito, so ano po ano yung napapansin niyo pong error, no? Ano agad yung nakita nating mali dito? The first thing that napansin ko dito, wala tayong in-indicate na preconditions or rule, no? Kung ano ba dapat yung amount niya, dapat ba si amount ay less than or greater than to 0 or is equal to 0. So, hindi siya nag-indicate dito. So, for self-confident approach, so nag-indicate siya ng volume if volume is less than 0, volume is equals to 0. Ayan. So, the process here is the program doesn't crash. Then, the cons is it's very hard to tell when something goes wrong. So, pag self-confident approach naman, hindi nga nag-crash yung program, kaso nga lang, how can you say that the program is true? Or how can you say that your output is true based on the process of your input? Then the third one, we have here the pedantic approach. So here the pros is you may know immediately when something goes wrong. While the cons is program crashes even when error wouldn't matter. So dito, medyo sensitive na yung program natin, no? So malalaman nyo agad kung mayroong error kasi si program natin, mag-crash siya even yung error natin is hindi ganun ka-fatal. So gumamit tayo ng assert command. Assert amount is less than or equal to volume. So we have the postconditions, races, assertions, error. So once na nag-error tayo dito sa code natin dito, matitrigger ngayon si assert command. So yeah, correctness. So checking loops, the correctness of a loop can be ascertained by making the following sequence of checks. So first one is to check that the preconditions implies that invariant is initially true. So yun, always remember that our preconditions must be always true. Then second is check that an invariant is preserved by the loop body. Then the third one is check that the loop invariant together with the terminating conditions implies that the post condition is true. Then after we run the program or we run our codes with the preconditions initiated, we make sure or our post condition must be true. Yeah. If the loop satisfies the above checks, then the post condition must be true whenever the precondition is true, provided that the loop terminates. Since it's possible for a loop to run forever, one more check is needed. So check that loop terminates. So kailan ba mag-end si loop natin? So dapat yung condition natin kung kailan mag-end si loop must be true, or else lifetime na maglo-loop yung ating program, no? Kapag hindi tayo nagbigay ng specific siya lalagyan ng hagganan or what you call this kung hindi siya mag-i-statement ng false, no? Then verification is the process of checking that a program is correct. So we need a specification before we can do verification. So the three main techniques to do verifications are, the first one is the code inspection. So look at the code and try to see if it does the correct thing. So we must so dapat very versatile tayo in testing stage of our program. Dapat lahat ng conditions i-try natin, no? Kung ano mangyayari, kung mag-error ba si program or hindi. Then the formal verification mathematically prove that every possible execution of the program satisfies the specification. Then just looking at your code is often the first thing to do when trying to find an error. Often, someone who did not write the code can more easily spot errors, or we call it pair programming. So code inspection is never a replacement for proper testing. So which is true, no? Syempre before we start testing, we must have a code inspection first, no? Kung reliable ba yung ating mga inputs. And correctness, two main kinds of testing. So we first we have the unit testing. So it tests functionality of individual components, methods, and classes. Then the second one is the system testing. Test overall functionality of the whole program. Both kinds of testing are necessary. So kung doon sa yung testing, meron ka na agad failure or meron ka na agad errors, dapat gawin mo siya na agad ng paraan. Hindi ka pwede mag-proceed sa system testing unless yung si unit testing mo ay okay na yung lahat, na-test mo na lahat ng unit mo. No, kasi kapag nag-system testing ka dyan, then meron ka pa rin error sa unit testing, mag-a-apply pa rin siya sa system testing and possibly maapektuhan niya pa yung ibang classes or methods na meron ka dun sa iyong system. Okay, for example, I have example here. Method add water under test. So class water glass to double volume and for max also is double. Then water glass is equals to double max. Then this that max is equals to max. Then volume is equals to 0. Then volume is equals to volume plus x. So the testing code, so water glass or G is equals to the new water glass, which is equals to 250. Then add water 0. Volume is equals to 0. Then add water 121. Then the volume must be equals to 121. And if you add water 3, the volume is equals to 121 plus the volume which is equals plus the water that is equals to 3. So yeah. Okay, sir. That's all for my report, sir.
Okay, so actually, reasoning about programs, no? Because as what our presenter mentioned, that we have the pre, we have the post, we have the invariants, and at the same time the correctness, no? We have some ways to verify your code, right? So the hard way, make up some inputs, no? If it doesn't crash, ship it, and when it fails in the field or attempt to debug. The easier way is the reason about possible behavior and desired outcomes. It construct simple test and exercise that behavior. Another way that can be easy is to prove that the system does what you have. We have the rep invariants are preserved. Implementation satisfies specification. We need also to consider the proof that can be formal or informal. No? The complementary to testing as what I mentioned by our presenter. Now, how about the reasoning about the code? So, sometimes now we are going to determine, for example, what facts are true during execution. There are certain programs now that we define x is greater than 0 or less than 0 rather. Where for all nodes n, no, that is n that next that previous is equal to n, for example. At the same time, for example, is an array A is sorted or negative x plus y is equal to say, or negative if yung null, then x multiplied by a is less than or greater than my x dot b. Now, this will be the common issues about concern about or reasons about the code. Now, in applications, now we ensure code is correct. How? Of course, by a reasoning or testing. We need to understand why code is incorrect also. Then, for forward reasoning, we need to know what is true before running the code. So, and at the same time, what is true after running the code? By giving a precondition and what is a postcondition. In application, presentation invariance holds before running code. So, does it still hold after running the code? So, for example, for precondition, our precondition, for example, x is even. So, x is equal to x plus 3. Y is equal to 2x. X is equal to 5. So, this will be the postcondition. Now, how about the backward reasoning? We know that if you want to be true after running the code, what must be true beforehand in order to ensure that? So, given a postcondition, what is the corresponding preconditions? of course, we need to reestablish the invariant at method exit. No? So what's required? What must the input have been? Okay? So for example, if our precondition is question mark and our postcondition is y is greater than 2x, same scenario, same given, now that x is equal to x plus 3, then y is equal to 2x. So therefore, x is equal to 5, something like that. So most commonly, we do it informally, okay, to compute this scenario. Okay, how about the forward versus backward reasoning? Forward reasoning is more intuitive for most people. Why? Because it helps understand what will happen when simulate the codes. No? If we can introduce facts that may be irrelevant to goal, we need to set of current facts may get large and takes longer to realize that the task is hopeless. For the backward reasoning is usually more helpful. It helps us to understand what should happen, given a specific goal indicates how to achieve it, and given an error gives a test case that exposes it. Okay, so a while ago actually our presenter gave us an example of a forward reasoning, no? So assuming by using an assert, no? You're familiar with assert, no? For example, x is greater than or equal to 0, then I is equal to x. Then z, for example, is equal to 0. So we are going to use a property which can hold, no, the value. No? So for example, we are using a control structure like while. No? For example, while is open parenthesis, of course, I is not equal to 0. Then, of course, based on the syntax of the while loop, no, let's begin. Z is equal to Z plus 1, I is equal to I minus 1. Of course, as I mentioned earlier, the Z is equal to Z plus 1. So what property holds here? No? For I is equal to I minus 1, what property holds also here? Then we end up with the assert x is equal to Z. That is for the forward reasoning. How about the backward reasoning? There are some techniques, no, for backward reasoning. No? So what we're going to do first is to compute the weakest precondition or the WP. There is our WP rule for each statement in the programming language because weakest precondition yields strongest specification for the computation and most commonly analogous to functional specification, right? Okay. Then we have a method calls, no? For preconditions. No? For example, no? If the method has no side effects, just like ordinary assignment, but if it has side effects, an assignment to every variable it modifies. No? Use the method's specification to determine the new value. Okay? How about the if statement? So, we have a lot of example actually of precondition. For example, if open parenthesis x is equal to 0, begin x is equal to x plus 1. Else, then x is equal to x divide x, and so on. This will be, the precondition is x is greater than or equal to 0. Okay? Now, how about the reasoning about loops? A loop represents an unknown number of paths, right? And case analysis is a problematic. Recursion present the same issue, and it cannot enumerate all paths. That makes testing and reasoning hard. So, in loops, we need to define the values and the terminations. What will be the values and what will be the terminations? So, what we're going to do is, of course, the pre-assertion guarantees. No? So, how about every time through loop? Then, since there are only a finite number of integers between x and y, for example, y will eventually equal to x. Then execution except the loops as soon as x is equal to y. And this will be the process of the loops for values and termination. In understanding loops by induction, we just made an inductive argument, no? Inducting over the number of iterations. Of course, computation induction is also considered. We need to show that conjuncture holds if 0 iterations. It assumes that it holds after in or after n in iteration, and show it holds after n plus 1. No? There are two things to prove. We have what we call partial correctness, and we had termination. When we say partial correctness, some property is preserved. Loop invariant is preserved by each iteration. For the termination, the loop completes. It means to say that the loop is complete. The decrementing function is reduced by each iteration. So the total correctness by a well-ordered set, we have not established that the loop terminates. Suppose that the loop always reduces some variable's value. So does the loop terminate if the variable is natural number, an integer, non-negative real number, boolean, or an array list? The loop terminates if the variable values are a well-ordered set, or every non-empty subset has less elements. In a looping statement, we have also a decrementing functions. In our data structure subject, during our undergraduate program, we have what we call d sub x, yung decrementing functions. D multiplied by x. Okay? That is in data structure that is maps state the program variables to some well-ordered set, and this greatly simplify reasoning about termination. Okay. Now, how about the choosing loop invariant? For a straight line code, the weakest precondition, the WP function, give us the appropriate property. So for loops, you have to guess the loop invariant and the decrementing functions. Then use reasoning techniques to prove the goal property. If the proof doesn't work, maybe you choose a bad invariant or decrementing function. So what you're going to do is to choose another and try again. Maybe the loop is incorrect. So what we're going to do is to fix the code. Then automatically choosing loop invariant is a research topic actually. So for those who wanted to do research, so choosing loop invariant is one research topic. So in practice, ako personally, I don't routinely write loop invariants. What I'm going to do is to write them when I am unsure about a loop and when I had evidence that a loop is not working. Because add invariant and decrementing function if missing. Okay? Write code to check them, understand why the code doesn't work, and reason to ensure that no similar bugs remain. We have more on induction actually, because induction is a very powerful tool. I don't know if you are familiar with base case. We have also an inductive step. Okay. How about the invariance proof methods? I don't know if you've heard already, but it is also covered with our. Do you have a do you have a discrete for BS computer science? I think you have BS discrete 1 and 2. At the same time, data structure at the same time, especially if you have design, analysis, and algorithms. Now, the essence of program proof methods, such as those described by, of course, it is difficult to explain concisely actually when it comes to the proof of methods. No? The main difficulty is the diversity of the syntactic formalisms which are used for representing algorithms. So this difficulty is even more evident when concurrent programs are concerned. So for example, although similarities and difference are intuitively observed between methods for proving invariance properties of parallel program. Okay? So it is difficult to compare them in abstract. No? Okay, then until now, the design of invariance proof method has been ad hoc and informal. No? The correctness of these methods is often established a posteriori, no? Posteriori. Rather, it is more advisable to formally construct a priori correct programs. No? Are you still remember the posteriori and the priori? For program verification methods. No? Although soundness and completeness proofs rely on simple and similar principles, they are often long and wearisome. No? Instead of always restarting from its scratch, the verification of program proof methods should be obtained from general purpose theorems. The manipulation of program proof methods should also be considered. No? So for example, I don't know if you still remember the Clark's method. No? For proving correctness of coroutines be considered as an optimization of the Clint's methods. Since simpler invariants are needed. The transformation of a program proof method in order to adapt it is to different language features is not always easier than the original and may be error prone. Okay? Rather, program verification method should be manipulated using correctness preserving transformation. Actually, by analogy, with what happened for programs, no, the stated arguments advocate in favor of a mathematical formalism for reasoning about program proof methods, in particular for constructing, explaining, verifying, comparing, optimizing, and transforming them. The mathematical model based on dynamic discrete transition systems illustrate it by means of an application to invariance proof techniques for parallel program, sharing global variables and synchronized by conditional critical section. Okay? I don't want to discuss in detail, but we have the operational semantics now during our design and analysis algorithm. That is for computer science now. Of course, we have also the fixed point characterization of invariance properties. No? A program include partial correctness, absence of deadlocks, and non-termination. That is properties of programs that can be proved by characterizing supersets of the set of states that can be reached during execution of these programs. Now, that is the fixed point characterization of invariance properties. We have also a fundamental sound and complete invariance proof method. No? We have also decomposition of a global assertion about program state into a set of local assertions. I don't know if you still remember the Galois connections, no? That is also under design in analysis algorithm, no? And the complete lattice of variance of fundamental invariance proof methods. No, we have a lot of computations, a lot of lattice, complete lattice, no, isotone operator, inequality can be restrict, no. The exist of isotone operators, no, if you're still inequality can be strict, inequality holds, no. So, given the operational semantics, the design of the invariance proof method consists in choosing either A or P, that it's how to set a program state are going to describe by assertion, no. In constructing an invariance proof method, the invariance proof techniques for parallel programs consisting of concurrent process sharing global variables and synchronized by conditional critical section. Okay? Several well-known methods are shortly reviewed and some of the possible alternatives are constructive, introduced, and it must be discussed. the using of a single global invariant, no, is used to indicate correctness, no, as mark of the ability to decompose the verification condition is not lost, no. However, the use of a single invariant is inadequate for large programs. Another one of the early attempts toward the decomposition of the global invariants can be found, no, in ASCROP, no. That is association and assertion about variables with its control state, and so on. Now, for the reasoning about programs, no, program correctness, no, we need to consider the GUIs in event-driven programming, no. So the programming graphical interface with swing, no, I think you know how to use swing. We have the top level, the J frame, the second level, J panel. The atomic components, we have the J level, J button, J text field, and so on. For the event-driven programming, we have the event handlers, no, yung implement the action listener interface. And we have the event publishers, offer a method to subscribe to an event. Now, how about the timer class, no? We need to implement action listener, like, and so on. So we have what we call during my time, no, during my doctor in IT, no, we have a given problem about the tower defense game, no? Implement a simple tower defense game. So actually commonly now available in a web, no? The solution for the tower defense game is now available actually on the web. You are familiar with Kahoot, right? That is GUIs in event-driven programming. No? So how can we know a program works correctly? And why do we care that a program works correctly? Because sometimes, no, even the output, no, we can get the correct output, but if even the code itself is incorrect, no, the way I will be able to present the code is incorrect. Even we could able to get the correct answer, no, but the sequence, the syntax, the logic itself is not correct, no. So what does it mean for a program to be correct? No, so a program that does not crash, do we say that this is a program correctness? A program that passes all the tests, could we say that is a program correctness? A program that matches its specification? Now, specification versus implementation. Correctness of a program is always relative to specification because the specification is a description of what the program should do and usually implicitly includes do not exclude. No? The implementation usually contains many more details than the specifications. So, how about the specification versus wait for a while. Okay, specification versus implementation. For example, in specification, no, method sum, yung the variable is sum, no, SUM, no, the total, the add, no. Method sum takes a non-null reference A to an array of integers and returns the sum of all values in A. So in implementation, of course, we need to use a data type that is int sum, open parenthesis, no, int, of course, yung the array value, no, yung braces, then A, begin, then end sum is equal to 0, then for int V is equal to A, sum plus is equal to V, then return sum. That this will be the implementation of a given specification a while ago. Now, how about the specification natural language versus symbols? The specification in natural language, no, the program returns the first prime number greater than the given number. Okay, so And we have some specification na symbol language, na symbolic language, which is better depends on the situation. Okay? Of course, as what we discussed earlier, the pre and post condition are important part of the specification for a method. No? Because a precondition is a property that should not hold or should hold, no, of the method's inputs before it is called. It responsibility of the one calling the method. While the post condition, a property that should hold of the method outputs after it is done. It is responsibility of the body of the method. So, for example, a precondition is A is not equal to null. So therefore, what we're going to implement is int sum and A, int sum is equal to 0. For post condition, no, we need also to get the looping for, no, using for statement or for that int v is equal to A, sum plus equal to B, and return sum. That is the precondition and post conditions for the method specifications. So a while ago, actually, our presenter discussed the pre and post condition in object-oriented programming. No? In OOP, the input and output of a method also include the object state before and after executing the method. So for example, specification, precondition, amount greater than or equal to 0. How about the implementation? Class, as yung sinasabi nga kanina ng presenter natin, no? Water glass, no? In volume. No? So for the post condition, we have new volume, old volume, and so on and so forth. Okay, so even the program verification must be also considered. No? The program verification is the process of checking that a program is correct. No? So we need a specification before we can do verification. So the three main techniques to do verification: code inspection, testing, formal verifications. Okay, so for the code inspection, just looking at your code is often the first thing to do when trying to find an error. So often someone who did not write the code and more easily spot errors. Now, that is what we call pair programming. Code inspection is never a replacement for proper testing. So, of course, later on, maybe somebody assigned to use to discuss the unit testing versus system testing. But to give you some basic information about this will be the two main kinds of testing actually, no? The unit and system. The unit testing cover the test functionality of individual components or the methods and classes. For the system testing, test overall functionality of the whole program. Okay? So again, for unit testing, we just test the functionality of individual components. Then, of course, some strategies for writing tests. No? We have the partition testing. We have boundary value testing, randomized testing, and we have a regression testing. So, the systematically testing your code is a good practice that every programmer should follow. So, test extensively, test early, test often, because big project can often have to 2 to 3 times more tests than actual code. Okay? Then, for formal verification, mathematically proving that a program is implemented correctly, often with the help of a computer. No? So we have model checking, theorem proving. So for formal verification, often takes a lot of effort, but it is the only way to guarantee that the program is implemented correctly. Okay? So in Java, no, we have program verifications. No? Java has no built-in support for program verification. Instead, we must rely on external tools to verify Java programs. No? So sometimes we are using very fast. I don't know if you're familiar with the program verification using very fast. Okay, so Agda also. We could able to use Agda. for program verifications. Dito na accept. Okay, so I think that's it for the topic of Sir Clark.